So in this video, we're going to ask the question, how fast is a cell as a computer? And it turns out it's a really interesting calculation. So look forward to talking through it. So I said in a previous video that cells are Turing machines, meaning that they are basically processing information. They have an internal state, they have a set of rules, they run a cycle of updating that internal state with the rules, and they are in fact acting as computers. This means that we can meaningfully talk about, well, how quickly are they processing information? And one way to measure this is just the number of bits per second. Now, without getting too far into the weeds of computer science and stuff, hopefully you've seen at least at some point that computers represent information as ones and zeros, and that having a string of ones and zeros lets you represent information. And we're going to just ask, how quickly can a bacterium do things with information? Now, you can think about this in a variety of ways. I'm going to think about it in kind of a simple way, and that is imagining a bacterium that's replicating its genome every 20 minutes. That's about as fast as an E. coli can replicate in the lab. That doubling time is 1,200 seconds. So every 1,200 seconds, a bacterium has to duplicate its entire genome. Now, the genome of an E. coli is 4.6 million bases long. So it's got 4.6 million A's, C's, G's, and T's. Each of these requires 2 bits to represent. And sorry for getting a little far into the weeds, but basically to represent an A, it would say be a 0, 0, a C would be a 0, 1, a G would be a 1, 0, and a T would be a 1, 1. The idea is each base, since there's 4 bases, you have to use 2 bits to represent each base. Okay, the point of that complicated thing is that the genome of that bacterium is 9.2 million bits. That's how big it is in information terms. And it's replicated every 1,200 seconds, which means that an E. coli replicates its genome at a rate of 7,700 bits per second. If the details of that calculation were confusing, don't worry about it. The idea here is now we have a number, 7,700 bits per second, which we can compare to other devices to ask how fast is our computer. And it turns out E. coli suck by this metric. So what I'm showing here is the number of bits per second that can be processed by this bacterium, 7.7 times 10 to the third. My cell phone operates at 1.1 times 10 to the 13th bits per second, so 10 orders of magnitude faster. And a supercomputer might operate at 1.7 times 10 to the 18th bits per second, so 15 orders of magnitude faster. So a cell phone or a bacterium is ridiculously slow as a computer. To give some intuition for this, a typical picture on my phone is about 5 megabytes, which would mean that if I had a computer running as fast as a bacterium, it would take over an hour just to load up the photo, right? Just to read each of the bits of information in that photo. So this is an extraordinarily slow computer. Now you might be saying, cool, bacteria suck. But you might also be saying, well, wait a second, bacteria are pretty darn small. What if we normalize to volume? What if we say, what's the size of a bacterium as a computer versus a supercomputer? And what if we say how dense is the computing, basically? So these are the volumes of a bacterium, of a cell phone, and a supercomputer. And hopefully what you appreciate is this number, 10 to the minus 18th meters cubed, is much, much smaller than 10 to the 5th meters cubed. So a bacterium is way smaller than, say, a supercomputer. And so if we then take the rate, the bits per second, and divide by the volume, what we see is actually bacteria are really fast. In terms of volume, a bacterium is computing at 7.7 times 10 to the 21 bits per second per meter cubed, where a supercomputer is a whole 9 orders of magnitude slower. So a bacterium is 1 billion times faster. Another way to put this is if we could build a supercomputer out of stacked bacteria, it would be 1 billion times faster than a normal supercomputer. So even though bacteria are slow in the absolute sense, per unit volume, they're actually really quite fast as computers. Another thing we can think about this is actually in terms of energy usage, right? So supercomputers and cell phones and bacteria all use energy. And we can ask, how quickly are they processing information per unit of energy? And it turns out that they're still really good. So this right here is showing the number for bacteria. And the key takeaway is this is 1,000 times faster or better, 3 orders of magnitude better than my cell phone. And I don't know about you, but I've seen over the years, cell phones have gotten more and more energy efficient, right? Engineers have worked really hard to squeeze every last ounce of computing energy out of the battery. And so what we're seeing is cells are still 1,000 times better or more energy efficient per calculation than cell phones are, for example. But it gets even cooler. And so it turns out there's a fundamental thermodynamic limit on computational efficiency. And I realize we are way deep into the weeds of thermodynamics here. So I'm just going to assert some things and then give an intuitive example to hopefully make it make sense. But there's this relationship here between heat and information. And we can think about this as the minimum amount of energy necessary to represent a bit of information. And so let's think about this in a simple thought experiment. Let's imagine we have a piston where there's gas on one side and there's no gas on the other. And we have a little spinning turn wheel here that when it spins, it's going to lift or lower a weight. Okay, now if we don't know which side the gas is on, how might we figure it out? Well, we could open a valve that lets gas flow. Gas will flow in here. That will cause this to spin. And in this case, it will lower the weight, right? This dq is the smallest amount of energy we have to change in the system to actually get a measurement of whether the gas is on the left or the right. The left or the right, maybe you could represent that as a 0 or a 1. So basically this is saying that there's a minimum amount of energy you need to measure a bit or to represent a bit. If you plug in numbers into this equation, what you get is that you can basically store the best you can do with information is 3.4 times 10 to the 20 bits per joule, whatever the heck that number means. But what's really interesting about that number, so that is basically the best computational efficiency that you can have energetically, is if you compare that to a bacterium, bacteria are getting awfully close to that limit. So this is the theoretical maximum, right? This is the best a perfect computer could do information processing wise. Log phase bacteria are minimally processing something that's only a few orders of magnitude away from this theoretical maximum. So basically bacteria are computing almost as energetically efficiently as possible, which makes a lot of sense, right? Evolution wants to maximize your ability to go and do stuff like a bacteria to process information, while also minimizing the energy that's spent. Okay, so what do we learn here? We said that first we learned is that cells compute pretty slowly in an absolute sense, but if they are shockingly compact, they're extraordinarily efficient if you just normalize to volume, and that they're actually computing with near perfect energetic efficiency. So, okay, that's all I got on that. Sort of a fun, interesting calculation. Hope you enjoyed it, and I will see you later.